Now we have the last talk, Super-Klein tunneling of Dirac fermion through electrostatic gratings in graphene. So you have 15 minutes for the talk and 5 minutes for the question. I'll let you know when you have 5 minutes left. So please go ahead.
Hey, thank you very much for the invitation. I'm going to talk about Super-Klein tunneling of Dirac fermions through electrostatic gratings in graphene. And this is a project done in collaboration with Francisco Correa, who is a co-organizer of this event, and Bit Jakubski from the Czech Republic. Well, let me start by saying that graphene is a two-dimensional material made of a single atom layer of carbon. At low energies, the charge carriers are modeled by a two-dimensional Dirac equation. And here I am presenting the two-dimensional Dirac equation that I will be working. Okay. In general, the potential term could have these four, well, could be decomposed in these four terms. The first term, proportional to sigma 0, is an electric potential. The term proportional to sigma 1 and sigma 2 is related to a magnetic field perpendicular to the sheet of graphene. And the last term, proportional to sigma 3, is related to the mass of the particle. In graphene, this term is usually equal to 0. For this problem, I will consider also that there is no magnetic field. So what I want is to find a electric potential term such that when you send a particle, well, first of all, such that we create a potential barrier, and this potential barrier should be transparent at a specific energy when you reach this potential in any direction. Remember that we have a two-dimensional problem, so we are going to play in the plane, and we can hit this barrier in any direction. So we want to have a transparent potential barrier. So the content of this talk is the following. First of all, I'm going to start with a time-dependent Dirac equation in one dimension. And I'm going to use the free particle. Later, we perform a Sushi transformation to create a time-dependent Dirac equation with a time-dependent mass term. Well, it is time-dependent and spatial-dependent mass term. Later, I will perform a big rotation to obtain the system that I am looking for. So I'm going to explain each transformation, and then I will give you one of the examples. So the supersymmetric transformation relies on the intertwining relationship, this one in green, where H0 represents a quantum system that I know how to solve. H1 is a new quantum system, and L is the operator that I need to find in order to perform this transformation. So for the initial quantum system, I'm using this time-dependent Dirac equation. Here, T is, T is time, and Z is a spatial coordinate. So I have a time-dependent system. To find the operator L, I need two solutions of the initial system that I am calling U1 and U2. Such solutions can compose, well, we compose a matrix using these two solutions as an entry in this matrix. So each row is one of these vectors. It's a two-entry, U1 is a two-entry vector. So when we place them like this, we have a matrix 2 times 2. And this matrix also solves the initial Dirac equation. Okay, next we are able to construct the intertwining operator L and the new system. As you can see, L and H1 contains the matrix U. So it is very important to find a useful matrix U, because many properties of U will be in H1 and also in L. The important to have L is because we can construct a solution of the new system given that we know a solution of the old system like this. So if we apply L onto a solution of H0, we obtain a solution of H1. Moreover, there is a missing state, an extra state of H1 encrypted in the matrix U. What we have to do is to find this matrix B with, and once we find the matrix B, we take each column of this matrix, and each column will be a solution of the new system. So in 2 slides, this is the time-dependent Sushi transformation of Dirac equations. About the big rotation, imagine that we have a time-dependent Dirac equation like the one right here. What we did is to make this change of variables. Z goes to Ix, I is the imaginary unit, and T goes to Y. So now we have X and Y as spatial coordinates. Then we multiply by sigma 3 and make a small rotation on the Dirac equation, and we obtain a new Dirac equation like this one. So this equation now is a 2-dimensional time-independent Dirac equation. Here we have a new potential, and the energy for this one is equal to 0. So let me give you some remarks about this big rotation. Because we perform, because we change C to Ix, the new Dirac operator could not be Hermitian in general, so we have to be careful on that. Second, the transformation also makes profound changes into the character of the potential term. So we started with a potential like this, and after the transformation, the electric potential goes to a magnetic term. Well, here we have a magnetic term goes to the mass term of the new system, and so on. But since at the end I want to finish with a system only with an electric term, what I have to notice is that the mass term before the big rotation goes to the electric term. So this term will be the important. What I have to do is to find a system B such that this term is 0, this one is 0, this one is 0, and this is different from 0, in order to find a potential that I want. Last thing, the big rotation describes the system at a single fixed energy, only E equal to 0. So let me show you the example. We start with the free particle model right here of a relativistic particle with mass m. So really simple. The solutions can be computed easily. Here we have the solution of the system. Now I'm going to perform the Sushi transformation. To do so, I need to select two solutions of the new system. So we selected this U right here, U sub 1. So it's a superposition of three solutions. We introduce these three parameters, S right here, C2 and C1. They are constants that will be useful later. We build the matrix U that we need to perform the Sushi transformation, like this. We found the intertwining operator. So, well, it is a complicated matrix. It's kind of long, but the important thing is that this function D2 right here depends on both time and the spatial coordinates. Moreover, it is important to notice how they depend on Z. Here we have this exponential, and here we have this other exponential. The other two terms depend only on time. And this is important because later we are going to make the replacement Z goes to IX. And we need to keep this function real. The new Dirac operator that arises is this Hamiltonian, this Dirac operator, where we only have a mass term, but now this mass term depends on the coordinate and time. So we have this explicit expression over here. D2 appears also right here. Next step is to make the big rotation. So we make the big rotation. Thank you. We make the big rotation symbolically here, and we finish with a potential, with a Hamiltonian in the form that I want. We have this electric term right here. In order to have a standard Hamiltonian, we need to have a real function right there. So we have to fix the one of the three free parameters like this. If we do that, we guarantee that this potential V1 is real. And just a small adjustment to have a better presentation of this potential. We added a constant M to the potential, and this will be my final potential. Why? Because now the potential when Y goes to infinity is equal to 0, something similar to the free particle. Another property is that this potential is periodic in Y. And we obtain, well, after adding that constant, the Dirac equation, time-independent Dirac equation for fermions in graphene at this specific energy, So what do they have? What are some special peculiarities of this equation? Well, first is that the potential can be attractive and repulsive depending on the free parameters that we introduce, C2 and C1. Second, well, in these pictures, the first picture is the potential given the, with this value of the parameters. We can see that it is a potential barrier, it's electric potential barrier. There is a bound state, and this is the picture of the bound state. If we vary the parameters, what we obtain is a similar potential barrier, but now with higher peaks over here. And we still have a bound state, or a bound state, or a state inside that barrier. If we decrease the parameters close to zero, we have bigger peaks in the potential, similar to a Dirac comb. We still have a localized state, but also if we send plane waves to this barrier, what we notice is that the plane waves travel, hit the barrier, and they continue in the same way. There is a phase shift, but the important is that there is no reflection. So we have a transparent barrier. Even if we bury these parameters, we still have this property, and this property will be maintained for any angle. Where else? And in any direction. So we have super-Klein tunneling in this electric potential barrier. So as a summary, we present a technique to obtain a truly two-dimensional electrostatic barrier that presents super-Klein tunneling. This happens only at a specific energy. In general, we could say that we have reflection, but at this specific energy, the reflected wave gets completely annihilated, and the waves incoming from any direction get perfectly transmitted. And as an additional solution, we found strongly localized states in this system. Well, thank you.
We thank Alonso. So it's time to your questions. Is there any question or comment? Mikhail has a question. You're muted.
You're still muted, Mikhail.
Sorry. Hello, Lance. At the very beginning, you discussed the general structure of 2 plus 1 dimensional Dirac equation, which corresponds to graphene. And there you mentioned that for general case of potential V0 xy, you told that the potential is perfectly transparent, but I'm confused. If I remember the corresponding paper of Katsnison with co-authors, they discussed the system in detail. And if I remember, the corresponding potential barrier is perfectly transparent when the particle arrives in the direction perpendicular to the potential. But if we have the angle, incident angle is different from pi over 2, there are some reflected waves. So maybe I'm confused. Can you comment on this point?
Right, you are completely right. Maybe it was something that I said wrong. But okay. Yes, in general, we have reflection, and it is difficult to find omnidirectional transmission. As you mentioned, the most common is only when you have perpendicular, well, when you hit the barrier perpendicularly. So no, this is not a general property. This is a property that I am looking for. So okay. I'm looking a special potential, electric potential barrier.
Yeah. Thank you.
Thank you.